Hello, and today's purpose of the day is I can graph rational functions. Okay, let's cover some of the basic characteristics of rational functions. The name of the function we are looking at is rational. The parent equation for rational functions are y equals 1 over x, similar to what we saw for inverse variation, or we could rewrite that as x times y equals 1. Or we could even say with function notation, f of x equals 1 over x. The general equation for rational functions is y equals a over x minus b plus c. And we'll talk about those different characteristics in just a little bit. Now let's go ahead and let's graph before we talk about some of the properties of rational functions. So if I were to graph this, the parent function y equals 1 over x, I need to plug in a few values into my table for x. So I'll choose values such as -2, -1, 1, and 2. So if I plug in -2, I have y equals 1 over -2, which is -1/2. If I plug in -1, that gives me y equals 1 over -1, which is just -1. If I plug in 1, y equals 1 over 1, which is just 1. And when I plug in 2, I get y equals 1 over 2, so 1/2. So let's go ahead and plot these on our graph right below. So you can see that I've graphed the few points that I put into my table, and I have what's known as a hyperbola for my graph. So a couple of the properties that we see here are we see two different asymptotes. We see a horizontal asymptote and a vertical asymptote. As I zoom in on my graph here, let's look at the horizontal asymptote. So I can see that both of my graphs for my hyperbola is getting very close to the x-axis, which would be at 0, but they're never actually going to touch. So that is at y equals 0, that is my horizontal asymptote. Now, if we go back and look at the general equation here, you can see that there's a plus c. Now, that c goes along with your horizontal asymptote. Here, our parent function that we graphed was y equals 1 over x plus 0, hence our horizontal asymptote was 0. So this could be, in other words, y equals c. So whatever that number is will be the horizontal asymptote. Now let's look at the vertical asymptote. I can see that on both of my graphs for my hyperbola, they're getting very close to the y-axis, but will never actually equal the y-axis. So this is my vertical asymptote. Again, I called my horizontal asymptote HA, and we have VA for vertical, so just shorthand. And this is at x equals 0. Now, you are going to see a relationship here with the denominator, this x minus b. Here for our parent equation, we just graphed, 1 over x, and the denominator there, that was just x. We didn't have a plus or minus anything, but really here, this is going to be part of our vertical asymptote. So if we were to set this up here, then, this would look like x minus b equals 0. Add b to both sides, x equals b. So whenever we have a value in our denominator, either adding or subtracting with our x, that is just going to be the vertical asymptote. Here, we just had 1 over x, y equals 1 over x. So if we just set that denominator equal to 0, x would equal 0, that actually is going to be our vertical asymptote. Some properties about rational functions are that we have a horizontal asymptote, and a vertical asymptote. And then both of the graphs to make this hyperbola have smooth curves. That is, they're somewhat like an exponential graph and a parabola in that they're not straight lines. Let's look at the domain and range. So for the domain, all the x values, we can almost, have anything we would like for the x values except what is our vertical asymptote. That's the only x value we'll never be able to actually hit on this graph, which would be at x equals 0. So here's the notation we're going to use for domain. I'm going to write in brackets, and let me make a better bracket here. And we are going to say for all x's such that x is not equal to 0. Close our bracket. So that means that x just cannot equal 0. And for our range, we will say, we'll make our bracket for all y's such that, now if we look at our y values, what is our horizontal asymptote? Well, what can y not equal vertically? That is 0, at y equals 0. So our range is for all y's such that y cannot be 0. And this is just this case. In other examples, this won't necessarily be the case that the domain and range can both not be 0. Let's look at a little bit more about rational functions. Goal number 1 that we want to complete, identify excluded values. This is otherwise known as finding the vertical asymptote. An excluded value is any value of a variable that results in the denominator being 0, since the division of 0 is undefined. So state the excluded value for each function. Hint, set the denominator equal to 0 and solve, because again that will result in being undefined. So on number 1, I am just going to set my denominator, which is x, equal to 0, and that is my excluded value. So my answer here is just x equals 0. All right, let's look at number 2. Now I'm going to set x plus 2 equal to 0 and solve. And so my excluded value here is x equals -2. And again, this is an excluded value because if I were to plug in -2, for this problem, I would have, for x, I would have -2 over -2 plus 2, and -2 plus 2 is 0, so -2 over 0 is undefined. All right, number 3, now I'm going to set 2x plus 1 equal to 0. Subtract 1, get 2x equals -1. Divide by 2, so this excluded value here is x equals -1/2. All right, and now our goal number 2 is to identify and use our asymptotes to graph. Okay, so step 1 says identify and graph the asymptotes using dashed lines. Remember, the vertical asymptote is finding the excluded value. That is at x equals b, and the horizontal asymptote is at y equals c. So let's look at our asymptotes right now. I'm going to find the vertical asymptote. So I'm going to set my denominator equal to 0 and solve. So if I set x equal to 0, I just get 0 for my vertical asymptote. Now for my horizontal asymptote, that's just setting whatever c is equal to y. So here that would be y equals -4. I'm going to go plot my asymptotes using dashed lines on my graph below to the left. Now that I've plotted those asymptotes, I'm going to look at step 2. Make a table, plot, and connect with a smooth curve. So now when I choose values for my x's to plug into my table, I want to choose at least 2 positive values and 2 negative values. So I'm going to just use the numbers as 1, 3, -1, and -3. Now I'm going to plug those in and figure out what the outputs would be. So if I plug in 1, I would have 3 over 1 minus 4. And 3 over 1 is just 3 minus 4 is -1. If I plug in 3, I will have 3 over 3 minus 4, and 3 over 3 is 1, minus 4 is -3. If I plug in -1, I have 3 over -1 minus 4, so that would be -3 minus 4, which would be -7. And last but not least, 3 over -3 minus 4 would be -1 minus 4, which would be -5. I'm now going to go plot those ordered pairs on my graph below. So as you can see on the graph below to the left, that I have my hyperbola in quadrants, well, 1 and 4, and then 3. So they are still they're still opposite of each other, and they again will not hit or touch those asymptotes. So let's determine the domain and range. So for the domain, again, I write in my bracket and I say for all x's such that x cannot be, and then whatever my vertical asymptote is here is 0. And then for my range, for all y's such that y cannot equal, here my horizontal asymptote is at -4. So that is my domain and range. And here are the characteristics and graph of the rational function y equals 3 over x minus 4. And please feel free to take a look at this extra example. We will be covering this example in class to recap the notes. Thanks for listening and have a great day. Please check Google Classroom for more information.